So this video is meant to fill in some of the gaps on where some of these equations come from the RC circuits. So in the lecture videos, you have your standard charging and your standard discharging circuits, and you have these equations that are given for how the charge builds up in the charging circuit. It's Q full and this 1 minus exponential thing, and then Q full is this. And then the standard discharging circuit, the charge is a kind of dropping exponential as the charge flows off. And we found also it was given that both of them have exactly the same current function and the same tau. But these are just sort of handed to you. And so in this level of class, we need to understand where these things actually come from. So let me quickly talk about that. So here's our discharging circuit. We have a capacitor which has some charge on it, and that charge is dissipating its energy through this resistor R. So the current is, this charge is flowing from here to here, and there's the current of it flowing. As far as how to attack this, well, first we would remember that there really are only two voltages in the circuit, a high and a low. So this is region A, high voltage, this region B, low voltage, and essentially the drop between the two elements is the same, right? So from A to B. And what we could do is we could write ourselves a nice little Kirchhoff's loop. So gain drop adds 0. And then we plug in, of course, our fundamental equations. The voltage across the capacitor is Q over C. That just comes from rearranging C equals Q over V. And then Ohm's law, the voltage across the resistor is I times R. So this is the equation that we somehow need to solve. Now it doesn't look like something that is much like what we see over here. So let me show you how you do that. First of all, there is a relationship between charge and current. It's literally the flow of this charge from here to here that is the current. So the current is just the rate at which the charge flows. Now there is one modification we do need to make to this, but that's the essence, right? The charge is literally the flow of the current. Now the one little tweak we need to make to this is the fact that for us, current, we want to keep it positive. So positive always. We just want it to be an amount. For us, negative current doesn't have any real relevance. For us, negative currents aren't necessary. We just have the current be positive. If we, for instance, when we were doing our Kirchhoff's rules type solutions, and we found a current was negative, that was just kind of a mistake. For us, we'd like our currents to be positive. However, if we were going to look at a Q versus T graph, and the charge was getting smaller, so I don't need to draw the whole shape, but let's say anytime the charge was getting less, this slope, which is dq dt, is actually negative, right? That's just the nature of a value getting smaller, is that it's negative. And so if that was negative, that would make this negative. We don't want that to happen. So what we do is we sort of give ourselves an extra sign. So we let there be a plus or minus sign in the front. And so if dq dt here was going to itself naturally be negative, we pick an extra negative. That'll make this positive. That keeps this positive. So whenever we have a charge that's actually decreasing, so when the charge is decreasing, we say I is negative dq dt simply to keep the current positive. Now if the charge is increasing, then of course we don't have that problem. The slope, which is dq dt, is positive already, and so we don't need any help, and so we'll use just the good old plus. So that's for the charge increasing. Now that's not the case we have right now, but we'll do that in a moment. So right now we're going to go ahead and plug in here. For I, we're going to plug in minus dq dt And that right there is our equation we have to solve. Now this is what's known as a differential equation. And you might not be there yet in math class, but usually after you take Calc 1, 2, 3, you take linear algebra and you take differential equations. Differential equations is an important class of equations. The thing that separates them out from the equations you might be more used to is that the answer to this, q, it's a function. So it's not a number, it's a function. There is some function of q that satisfies this equation. When you take that function, divide by c, and then minus, and then take the derivative of that same function times r, you will get 0. Okay? So as far as how to solve for differential equations, you're going to take a whole class in it. They can get very complicated. In fact, some differential equations aren't even solvable at all. But this one is actually really simple to the point where the techniques, this is something you might do in like literally the first week of differential equations class, because you've already seen the techniques to do this. So what I'm going to do is I'm going to take that equation and I'm going to rearrange just with algebra. So q over c minus negative dq dt times r equals 0 can be rearranged into this equation. I'm not going to bore you with the algebra, but this is what it ends up being. Okay? So, if you ever see that, you should be looking, and this should hit you incredibly strongly, anytime you have that the rate of something is tied to the amount of that something itself. That is literally the definition of an exponential. So we are expecting an exponential function. Anytime you see that the rate itself, so how rapidly the charge is changing, is directly related to the amount itself, you'll get an exponential. So for instance, when you have a lot of charge on the plates, it'll also flow off very rapidly. When you start to have very little charge on the plates, the rate will also decrease. And when you have 0 charge on the plates, the rate will be 0 as well. Okay? So that's something to take with you. This happens all the time in math and engineering. When you see that anytime a rate is proportional to the thing itself, that's going to be an exponential. So how do we solve this? Well, first, let's go ahead and call RC tau, just as an abbreviation. And then what we'll do is we'll bring all the Q stuff to one side and all the non-Q stuff to the other side. This is what's called separation of variables. You're kind of segregating all the Q's over here and all the non-Q stuff over here. And this is, again, this technique is called separation of variables. And that's just a temporary thing. It helps us to do this. We're now going to integrate both sides. And just so we don't have to deal with all the plus c business, let's just go ahead and put in our limits here. Our time, this is the time integration, we're going to start from 0 time and go to some random time. And here we're going to start with our initial charge and we'll go to some general time later. So what we get here, this is natural log, and then putting in the limits. And then over here, of course, minus 1 over tau is a constant, so integral of dt, we just get t. And when we solve this, we get exactly the equation that we said we get. So the thing that was just handed to you before, the standard discharge equation, that's where it comes from. Now, am I going to expect you to do this kind of integration on an exam? No, because most of this is really math. I'm not interested in you doing this kind of integration stuff. But you will find that many of the techniques here that we talked about will be useful. So for instance, we had to understand Kirchhoff's laws to do this, okay? We had to understand the fundamental voltage equations for each to put them in here. I have even, on exams in the past, have asked you to set up this equation, not just to then manipulate it and solve for Q, but to show me the kind of the end of the physics, which is, okay, could you set up the equation, plug in all your stuff, and then say, okay, if someone knew how to solve the differential equation, then that would proceed from here, okay? It's also useful because knowing the relationship between current and charge, if you have the charge function, you can get the current function. So let's do that right now. Remember, I, for us, was minus dq dt. So let's go ahead and take the derivative. There's a minus sign in the front, and then we take the derivative of this stuff. Well, derivative of an exponential is just an exponential. That's one of the beauties of taking that derivative, and then just the derivative of what's inside, so that's up here, so that'd be minus 1 over tau. Here, notice that this negative wipes out this negative. Remember, I said that dq dt itself was naturally going to be negative, and that's the very reason why we wanted this negative here, so that we didn't have to deal with a negative current, because that's annoying. So this current will come out positive. So these two will wipe each other out, and as advertised, we will get a positive current function. Now the only thing that makes it look different here, of course, we learned that the current function before is this. This isn't quite the same, so it would be if I initial was equal to Q initial over tau. Then, of course, we would get back what we should. So, of course, we just have to address, is this true? So let's check that. So Q initial over tau, well, tau is RC. And I'm going to take this, Q over C, that's VC initial, that's the voltage across the capacitor initially, Q over C. And then let me remind you that the voltage across the capacitor and the voltage across the resistor are one and the same thing. So I'll switch that over to the voltage across the resistor initially. And at this point, you recognize Ohm's law, that is the initial current. V over R is current. So yes, this is true. Okay? So there you have it. Where these two formulas came from. And again, not that I would necessarily expect you to integrate here, but there are several kind of useful techniques here that will come up on the homework. So for instance, this trick right here, taking the derivative of your charge function to get the current function, that's a really good trick to know just alone. It's very useful. So the only thing we have to do from here is kind of use the same techniques for the charging function, that standard charging equation. So again, you have battery, resistor, currents going through it, and depositing charge on your capacitor. And so writing down our Kirchhoff's loops, we go gain, drop, drop, gain, drop, drop. So there's the voltage waterfall. If you wanted to imagine it, gain, drop, drop. And then we plug in again Ohm's law. Definition of capacitance gives us V equals Q over C. And then remember this time, since this is going to be charging, we can dq dt itself is going to be positive because the charge is increasing, so we can just pick a minus sign in the front there. We put that in here, and there it is. So from here, you can just rearrange this. And let me just kind of cut to the chase. You just do some rearranging until all the Q stuff is on one side and all the non-Q stuff is on the other side. You get something like this. And now, again, you've got this in, all the Q stuff is over here, separation of variables, all the non-Q stuff is over here. Oh, whoops, I forgot. This is actually dt, excuse me. And now I'm jumping the gun there. I'm going to integrate both sides. I'm going to go ahead and go past RC here anyway because it's a constant. And remember that we'll kind of call this tau. And so over here, just to avoid the whole plus C business, we're going to integrate here time from 0 to t. And here, remember, we're charging here, so we're going to start from 0 charge and go up to some random charge Q there. And so when you do that, you get natural log. This is a natural log. You evaluate it at the top bound, Q minus that stuff, and then evaluate it here, so that's 0. minus that same stuff. You can do a u substitution here if you don't see that. It's pretty simple. And then over here we'll of course get the same thing, and if you rearrange that, you will get exactly the same charging function for the standard charging that was advertised. And if you, again, want to then take the derivative of it, you will get, and I'll let you try this, you will get this. Again, it doesn't quite look like it should. We're expecting this, but the question, of course, is this really the initial current? So let's quickly show that over here. If I plug in tau equals RC, we get the C's cancel, and of course here, this is just the battery EMF over R. Well, remember that when the capacitor is uncharged at the very beginning, it has no voltage drop, so the entire voltage drop is across the resistor. So this is VR initial, and this, of course, is I initial. So there you have it. Those are where the equations for the exponential charging and discharging equations come from. Again, it's not that I would necessarily have you do this separation of variables and integrate, but there are some very useful techniques that I'm using here that I will figure out a way to kind of incorporate in some of the problems.